Okay, so we're in section 11.2 now. We're dealing with the topic of series. And like we said at the beginning of 11.1, chapter 11 is all about sequences and series, but mostly series. So this is where we're getting into kind of the meat of chapter 11. First, we need to define what a series is. So if you have an infinite sequence, like what we talked about in the previous section, a sub n, then we can get an expression of the form a sub 1 plus a sub 2 plus a sub 3. Basically, we're adding all of the terms of this sequence. So we call this a series. You can basically think of a series as a sum with an infinite number of addends. And it's a lot more convenient to write this using summation notation. So this is summation notation right here. This is something that you should have seen before, but if you haven't, a quick review on how this works. It's this symbol right here, we call this a summation or a sum. And basically what it does is it takes this thing here, treats it as a formula that we plug numbers in for. So down here it says n equals 1. That represents the first thing I plug in for that n right there. And then what we do is we count our way up to the number on top. Now in this case, there's an infinity up there, which means this thing is going to have an infinite number of terms. So I'm going to plug a 1 in, and then I'm going to plug a 2 in, and then I'm going to plug a 3 in, and I'm going to add those every step of the way. So here's an example of a series that we get from summation notation. It's the sum from n equals 1 to infinity of just n. So when I plug 1 in for n, I get 1, and then I count from there. 1, 2, I plug in a 2. Gives me 2. Plug in a 3, gives me a 3, and so on. This is the series 1 plus 2 plus 3 plus 4 infinitely. This series does not add up to a finite number. This shoots off to infinity. It gets bigger and bigger and bigger. It never slows down, never stops. So this thing does not have an actual finite sum. But other series do, and here's an example of one that does. This is the series where the formula, the thing that I'm plugging n's into is 1/2 to the power of n minus 1. So notice if I plug a 1 in, 1/2 to the 1 minus 1, that's 1/2 to the 0 power, that's 1. And then 1/2 to the 2 minus 1, which would be 1/2. And then 1/2 to the third power is what would come next, or the second power, that's 1/4. Then to the third power, 1/8, and so on and so forth. So I get this sum where each new term is 1/2 of the term that came before it. There's a geometric way of looking at this to see why this doesn't add up to, why this doesn't just shoot off to infinity. This comes out to something finite. So if I take a rectangle, a 2x1 rectangle, and I shade in exactly half of that rectangle, then the area of that would be 1. Then that's got that 1 right there. That area is going to represent like the 1 in this first term of our series right here. Then if I look at what's left, what's going to remain is this other rectangle over here. If I shade in half of that, which you're seeing in orange here, that would represent the 1/2, because the remaining area would be 1, so half of that would be 1/2. Then I have this rectangle down here that remains. It has an area of 1/2. If I shade in half of that, I get 1/4. And you can continue this on and on and on, and each new part that you're going to shade is half of the area that you shaded before it. But if I never completely shade in all that remains, I'm only shading in half of what remains each step of the way, then I'll never actually fill this rectangle up, which means the combined area of all of these little pieces is less than 2. But the little bit that remains is getting smaller and smaller and smaller. You can't even see it anymore in this picture. So that means the little bit that is causing the combined area to be less than 2 is shrinking off to 0 as n goes to infinity. So that suggests that this sequence or this series adds to +2, which is a little bit weird to wrap your mind around when you think of the fact that it has an infinite number of positive terms, but it adds up to a small number like 2. Okay, So we can show that more rigorously later without using this geometric argument. But let's continue on. So another example of a series that we know adds up to something finite comes from how we understand decimals. So for example, the repeating decimal, or we use the term non-terminating as well, meaning a decimal that goes on forever. 0.333333 on forever. We know what this means by interpreting this decimal notation. This is the tenths place, and this is the hundredths place, and this is the thousandths place. We have 3/10ths, 300ths, 3,000ths, which we can represent this way. This decimal means the same thing as 3/10ths plus 300ths. Notice I'm writing that as 3 over 10 squared, plus 3,000ths, which we can write as 3 over 10 cubed, and so on and so forth. This thing can be written in summation notation this way. Notice I have 3 times 1 over 10 to the power of n. That's accounting for those powers right there. That's an infinite sum. It has an infinite number of positive terms, but we know it adds up to a finite number. It adds up to 1/3, because this is the decimal representation for 1/3. So these series can add up to finite values, or they can not, and we want to know when it does and when it doesn't by establishing some tools. So to make this a little bit more formal, how do we think about the sum of an infinite series? Well, what we do is we start with what's called a partial sum, the nth partial sum. In a series, we define the nth partial sum to be the sum of the first n terms of that series. And we denote that partial sum by Sn, like this. So notice S1, in a general series like this one, where the terms are an, S1 would be A1. S2 would be A1 plus A2. S3 would be A1 plus A2 plus A3. So you can see how each partial sum adds up the first n terms of your series for whatever subscript I'm using for n. What I can do is compute these partial sums, and then they form their own sequence, because this will go on forever, right? There's infinitely many terms in this series, so there have to be infinitely many partial sums. And that sequence of partial sums, if it converges, then we define the limit of that sequence of partial sums to be the sum of the series. That's how we make this a little bit more formal. So if that series has a limit, if that sequence of partial sums has a limit, and we say that that's what the sum of the series is, then we say that that series is convergent, or we say that it converges. If that sequence of partial sums does not have a limit, then we say that the series diverges. So that's what this definition is saying. Notice we're using the same terminology that we used in 11.1 for convergent and divergent sequences, and that's because we're thinking of the sum of a series as a sequence of partial sums. So we get to use that same terminology. All right. So here is an example. We want to determine whether this series converges or diverges. And if it converges, we want to find what its sum is. So there's a bit of a trick to this one. Notice that your denominator here is a quadratic, and it's one that's pretty easy to factor. So if I write my an as 1 over n squared plus 3n plus 2, that thing factors to n plus 2 times n plus 1. Okay, and that's pretty easy to verify. You should know that. This thing, if I used a partial fraction decomposition on it, I could write that as, how would we do that? That would be 1 over n plus 1 minus 1 over n plus 2. And to verify that, if I multiply the numerator and denominator of this by n plus 2, I would get an n plus 2 up here. Multiply this by n plus 1 on the top and the bottom, I get n plus 1 here. When I subtract them, I'm just going to be left with a 1 on top. but the denominator would be this. You can, and we've talked about partial fraction decompositions. You can go through, all the steps of finding that, but it shouldn't be too hard to verify that this is the same thing as this. So that's going to help if I think of it this way. So let's compute some of the partial sums now. S1 is just the first term. So notice this series starts at 0. We plug 0 in for n first. So if I plug a 0 in here, I'm going to get 1 over 1 minus 1 over 2, so 1/2. Okay, and I'm not gonna bother simplifying it. I'm actually gonna leave it this way, and it'll become apparent why I'm doing that in a second. What is S2? Well, remember, S2 is adding the first 2 terms of our series. We already found the first term. It was this, 1 over 1 minus 1/2. The second term of my series is going to come from counting up from 0. So now I'm going to go up to 1. I plug a 1 in for n, and I'll get 1/2 minus 1/3 plus 1/2 minus 1/3, right? What about S3? What is S3? Well, I have my first 2 terms of my series already worked out. So what would the third term of this series be? From 0, I go to 1, then from 1, I go to 2. I'm plugging a 2 in for my n here. 1 over 2 plus 1, that's 1/3, so plus 1/3. And then I'm going to get minus 1/4 right there. And do you see what's happening with these partial sums? I'm getting cancellation happening. So negative 1/2 and positive 1/2. Here I get negative 1/2, positive 1/2, negative 1/3, positive 1/3. In fact, if we kept going, what you're going to see happening is all of the terms in the middle of each partial sum cancel out, and I'm only going to be left with the first number here, which is 1, minus this final value here. Now, what if I did this all the way down to S sub n? Well, we're going to get 1 over 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3, and this is going to keep going, minus ... until eventually I get to what? Well, notice here, the very last term that we ended up with, if I compare it to my subscript, I get 1 over that value minus 1 over something that's 1 more than that value. So here I would get plus 1 over n minus 1 over n plus 1. But we know that all of this other stuff is going to cancel out, and really this is just 1 minus 1 over n plus 1. Now think about the fact that this n is going to infinity. If n is going to infinity, this term right here is going to go to 0 because I get 1 over a very, very large denominator. So that's just going to leave me with 1. The sequence of these partial sums is going to 1 as n goes to infinity. And so that means that the sum of this series is 1. Okay, this type of series has a name. We call these telescoping series. And the reason for that is if you can imagine like one of those old collapsible telescopes that you see in like pirate movies, they may start out, fully elongated like this, but then you can squish them down into this little compact thing. And that's kind of what's happening here. Each partial sum telescopes by canceling all of these middle terms out, and we're only left with the first and the last term. Most series that we are going to come across don't do this, but when we find the ones that do, it's an easy way to see that these converge. Okay? Another really important example of a series that we come across a lot, all throughout chapter 11, in fact, is what's called a geometric series. And this is actually something you typically talk about as far back as intermediate algebra. A geometric series is a series of this form, a plus ar plus ar squared plus ar cubed. So basically what this is you have some first term, and then every term that comes after that is obtained by multiplying the previous term by some constant r. And it's the same r that you use for each new term. So notice ar squared is what I would have gotten by taking this ar and multiplying it by r. And then ar cubed is what I would have gotten from ar squared and multiplying it by another r. That r is called the common ratio of the series. And the reason we like geometric series is because there's convenient formulas for finding what they sum to if they sum to anything at all. So first of all, notice that if my common ratio is 1, if r is equal to 1, then the nth partial sum of my series is just going to be a plus a plus a plus a, because all of these r's are going to be equal to 1 when I raise them to whatever power I'm raising them to. There's a total of n of these here, so this is na. As n goes to infinity, this expression is going to go to either positive or negative infinity if a was not 0. If a is equal to 0, then this is of course equal to 0. But if a is non-zero, then this expression is going to go either to positive or negative infinity, which means that the series would diverge in that case. Okay, so we're going to assume that r is not equal to 1 and see if we can figure out how to know if a geometric series is going to converge or diverge. So we do this by looking at the partial sums again. The nth partial sum of a geometric series would look like this: a plus ar squared plus all the way out to ar to the n minus 1 power. It's n minus 1 because if you notice, the first term doesn't have an r in it. So I could technically call this ar to the power of 0. It's my first term, but the power is starting at 0. So the power is 1 less than the number term that I'm talking about. So if I want to go out to the nth term, then my power should be 1 less than that, n minus 1. Now we're going to do a little trick with this. I'm going to take this series, or this partial sum, and multiply the whole thing by r. In fact, I'm going to multiply both sides of this by r. So I get rs to the rsn is equal to, now notice if I multiply all of these terms by r, this a becomes ar, and this ar becomes ar squared. It's like taking all of these terms and shifting them over to the right by 1. And then my ar n minus 1 is going to become ar to the power of n here. Next thing I'm going to do is subtract these. I'm going to take this partial sum and subtract it from rsn. So on my left side, I get sn minus rsn. I get this. On my right side, I get something similar to what we saw with our telescoping series. These terms will all cancel. The ar minus ar goes to 0, ar squared minus ar squared goes to 0, and so on and so forth. And I'm only left with this a minus this arn right here. So I get this, okay? Now I can factor that sn out, so it looks like this, and then divide by the 1 minus r that remains so that I can get a formula for my nth partial sum. This thing right here, a times 1 minus r to the n, all over 1 minus r. So if I want to see if the geometric series converges or diverges, I want to see if this nth partial sum goes to some finite limit as n goes to infinity. And the only place where n shows up in this formula is this r to the n power. You may remember an example that we did in 11.1 where we looked at the sequence of terms r to the power of n, and we said that this thing will only ever converge if r is between -1 and +1. In fact, in that example, we said r could equal +1, but on the previous page of these notes, we said that we've already considered r equals 1, so we're not considering it again here. So if r is between -1 and +1, then this thing, according to what we did in 11.1, will go to 0. And if r sub n goes to 0 as n goes to infinity, then this just becomes a up on top. So I get a over 1 minus r. This thing is a really important little formula because this is always going to be the limit of a geometric series if that common ratio is between -1 and 1. Now, if r is greater than 1, then if you look at the series here, I can factor an a out of this nth partial sum, 1 plus r squared plus blah, 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 plus r to the n minus 1 with an a on the outside. This looks similar to the nth partial sum of that series, r to the power of n, where we start that sequence. The series, sorry. Now the sequence r to the power of n diverges, so the series would also diverge in that case. And what that tells us is that the geometric series shown here will only be convergent if r is between -1 and +1. Another way of writing that is that the absolute value of r is less than 1. And here's what its sum is. We just figured this out. If the absolute value of r is greater than or equal to 1, then the geometric series will diverge. So as a final example before we wrap this video up, let's find the sum of this series right here. 4 minus 4/3 plus 4/9 minus 4/27. This thing is a geometric series. And the reason I know that is because if I compare each term to the one before it, I'm multiplying the previous term by 1/3 each time. So this 4 I multiplied by 1/3. 4/9 is what I get by multiplying 4/3 by 1/3. Except that's not completely accurate, because if I'm just multiplying by 1/3, that's not accounting for the fact that I'm changing signs from positive to negative each time. So in reality, I didn't multiply 4 by 1/3. I multiplied it by a -1/3 to get a -4/3 here. And then if I multiply that by another -1/3, then I'm going to get a +4/9. And then you can kind of see that pattern continuing here. So in this case, my first term, which we call a in this formula up here, was 4. And the common ratio that we just figured out is -1/3. That value is, in absolute value, it's less than 1. So the absolute value of -1/3 is just 1/3, and that's less than 1, which means that this series converges. Because it converges, I can find its limit using this formula. So 4 minus 4/3 plus 4/9 minus 4/27 plus ... That's series. It's equal to a over 1 minus r, or in this case 4 over 1 minus -1/3. That's 4 over 4/3, which is just 3. So this series adds up to 3. And I'm just using this result to find that. Okay, so that's going to wrap it up for this video. We'll keep looking at series in the next video.